Hello everyone, this is Dr. Lennon, and today we're going to talk about differential equations. So we're going to introduce them, and then we're only going to talk about one type that we're able to solve, which are separable differential equations. There are many ways to solve differential equations, and generally after calculus you would take a whole class on differential equations where you'd learn about all sorts of different methods, integrating factor, separable equations, which we'll do here, and then check certain conditions to see if differential equations are exact or not, things like that. And then even after that, you can look at differential equations, partial differential equations, once we start concerning ourselves with more variables. So technically what we're looking at here are separable ordinary differential equations. But anyway, so let's jump in. So what is the idea here? The idea is that differential equations involve more things than traditional equations. So differential equations which if I abbreviate it, I will abbreviate it by DEs like this, are equations that involve constants and variables like normal equations that we've dealt with so far, but these will also contain functions and even derivatives of functions. So we just don't have constants and variables anymore, we also have functions and derivatives. So in algebra, as we said, equations typically involve only numbers and variables. And the solutions to these types of equations are just given by numbers. So we're going to contrast that to differential equations. So in contrast, the solution to a differential equation will actually be a function. So let's consider a differential equation, and I'll show you one possible solution and we'll verify that that is indeed a solution. So example, let's consider the dE y prime equals x times y, and verify that y equals e to the x over 2 is a solution. So in this case, x is acting like our variable, y is acting like our function. It's given by a formula in terms of x, and y prime is actually a derivative of that function. So basically what we want to do, we know what x is, we know what y is, so xy would just be x times e to the x over 2, so we want to find the derivative of y. So we're going to use the chain rule to do that. So use the chain rule to find y prime. So the inner function is going to be, the function that's the solution is e to the x squared over 2, not e to the x over 2. So the inside is going to be that exponent, x squared over 2. And the outer function would be e to the t. So then the derivative of the inside would in fact be x and the derivative of the outside would be e to the t again. So our derivative here, y prime, is just x. So the derivative of the inside times the derivative of the outside, but we replace the outside with the original inside that it's a placeholder for. So it'll be e, and then change t into x squared over 2. And notice that is exactly x times y. So note that xy is also equal to x times e to the x squared over 2. So hence y equals e to the x squared over 2 is a solution to the dE. So I kind of just gave you the solution there and said, okay, go ahead and verify that's the solution. But usually that's not how things work in math. We'd like to know how you would come up with that. So how would we ever guess y equals e to the x squared over 2 is the solution, technically is a solution, by looking at y prime equals x times y. So how would you come up with that? Well, if we're thinking in terms of functions, it might make more sense to rewrite y prime as dy over dx using the Leibniz notation. And then we've got this as x times y. And, well, one thing, we could move the differentials around. So multiply both sides by dx, and we end up with dy equals xy times dx. And then we can separate the x's and the y's. We could divide both sides by y. And we would end up with 1 over y times our dy on the left, and we would just have x times dx on the right. And since we have differentials there, we can get rid of those by just integrating both sides. And once you do that, you end up with the natural log of the absolute value of y is equal to x squared over 2. And technically there would be plus a constant here. We can adjust for that, but if we just say, okay, suppose the constant is 0 for now, then we could raise both sides. We could exponentiate both sides with base e, and we would see that y is equal to e to the x squared over 2. And we get our solution. So as you can see, via multiplication and division, we were able to put all the x's on one side and all the y's on the other side. That's why this is known as a separable equation. So this technique works because we are able to separate the variables x and y. So these are the kinds of equations using this technique that we'll be able to solve. So let's go ahead and define what property they have to satisfy. So we say a separable dE is one that may be written in the form dy over dx equals some function of x, g of x, times some function of y, f of y, where g is a function of only x and f is a function of only y. So again, like with most things, you've verified that one thing's an example. We have the definition. We kind of understand the technique, but the only real way you're going to master the technique is by going through lots of examples. So let's go ahead and do that. I will say for the examples that I'll do here, I will stop once we have integrated, but in general, some teachers or some online homework sets will require that you actually solve for y, so that's a function, right? In terms of writing things as a function, usually what it means is you can write something as the independent variable and the dependent variable. And the dependent variable is usually able to be solved for. So we'll look and see how that's the case. So we'll say solve each dE. And we'll do a few examples here. So A, let's say we have dy over dx equals xy squared. So this is not too far off what we did previously. So again, we separate the variables by first multiplying by dx. So we have dy equals xy squared dx. So our x's are on the right. So to move the y squared to the left-hand side, we'd have to divide both sides by y squared. So we have 1 over y squared dy would equal x dx. We've just divided both sides by y squared. Integrate both sides, and we would have minus y to the negative 1, because y to the negative 1 over y squared is the same as y to the negative second. And when you integrate x, you get x squared over 2, and then in general plus a constant. So this would look like minus 1 over y equals x squared over 2 plus a constant. So I will stop here, but in general they might ask you to solve for y. So to do that, you'd have to multiply both sides by negative 1 and then take the reciprocal. So you can go ahead and do that. If we look at a practice homework set, I'll go ahead and go all the way to the end, but for now I'll just leave it in this form. Okay, so for B, let's go ahead and look at dy dx is equal to x times e to the negative y. So again, we're doing the same thing. We start by multiplying by dx. So we have x e to the negative y dx. And remember, e to the negative y is the same as 1 over e to the y. So really what we can do is we can just multiply both sides by e to the y. And e to the negative y times e to the y is e to the 0, which is just 1. So we have e to the y dy. And we'll just be left with x dx. And then we're ready to integrate because we only have x's on the right and y's on the left. And so this would look like e to the y, and it will equal x squared over 2 plus our constant. And again, we would stop there. You could have also thought of the second step as dividing by e to the negative y. And so again, you'd get cancellation on the right-hand side, and on the left, dividing by e to the negative y is the same as multiplying by e to the y. C, let's say we have x squared plus 1 times y prime equals xy. So this is just using the normal notation. So typically what I would do is I would first change that y prime into a dy dx. These tend to work a bit better if we are just utilizing the Leibniz notation, so we can see where the differentials belong. So again, I'm going to multiply both sides by dx, so I have x squared plus 1 dy equals xy dx. And so what I need to do is I need to get my x's on the right and my y's on the left. So what I'm going to do to move my x's over is I'm going to divide by this x squared plus 1. And on the right-hand side, I'm going to want to divide by y. So I'll also divide by y. So I'm dividing by x squared plus 1 times y on both sides. So the y cancels on the right, and so on the left, I've just got 1 over y dy. And on the right-hand side, I've now got this x over x squared plus 1 dx. So I've separated the y's to the left and the x's to the right. Again, this is done via just division in this case. And Once we do that, we have the natural log of the absolute value of y on the left. And on the right-hand side, this is actually going to require a u substitution, but I'll leave that to you if you want to work out the details. But I will tell you it's 1/2 times the natural log of the absolute value of x squared plus 1 plus our constant. You might even be able to see that u substitution because if your inside is x squared plus 1, your derivative from the chain rule would be 2x, and the 2 would cancel with that 1/2 in front. So this part is done by u substitution. Okay, so let's do another one. Let's say, what if we have d y squared plus x y squared dy over dx equals 1. Well, first thing here is to separate the variables. It doesn't look like we're able to do it right now because the x's and y's are kind of bunched together, but we do see a greatest common factor of y squared that we can pull out. So if we factor out y squared, we're just left with 1 plus x dy dx equals 1. So then we can go ahead and multiply by dx as usual. So we have y squared times this 1 plus x dy equals dx. And then we can see we really just want to divide by 1 plus x. So we'd be left with y squared times dy equals 1 over 1 plus x times dx. And now we're ready to integrate both sides. So the integral of the left-hand side, the antiderivative is y cubed over 3. And on the right, it's just going to be the natural log of the absolute value of 1 plus x plus a constant. So as you can see, generally these are not too hard, just a little bit of algebra to separate the variables. And then once you're finished with that, you're going to have to find an antiderivative of a couple of different things. That can require some of the techniques that we've done. In the trickier examples, it will involve a u substitution or an integration by parts. Sometimes it will just appeal to basic rules. So far, we've only seen one u substitution. Okay, so let's make a remark. So, in general, the particular function that is a solution to a DE is only known up to a constant. We always had all these plus c's all over the place, or in some cases you might, if you solve for y, might be multiplying by some constant. However, if we know a point on the solution, we can find the exact value of the constant. So there's some terminology here. A DE along with a function value, which is sometimes called an initial value, is called an initial value problem. And this is often abbreviated IVP. So solving these will amount to doing the same thing we were doing, but in the end plugging in to find the value of the constant in question. So let's go ahead and look at that. So example here, solve each initial value problem. Which, we're abbreviating IVP. Okay, so A, let's say we have dy dx is equal to x over y, and we know y of 0 equals -3. So that means if you plug in 0 for x, the value of y is -3. So again, this is a very easy one to separate. We just end up with y times dy is equal to x times dx. So we can integrate both sides there, and we end up with y squared over 2 is equal to x squared over 2 plus a constant. And now we can plug in the function value to find the actual value of c. So if you plug in 0 for x and -3 for y, what do we get? -3 squared over 2 will equal 0 squared over 2 plus a constant. So we see that 9 over 2 is the value of our constant. So our actual curve, that's going to be our solution, is y squared over 2 equals x squared over 2 plus 9 over 2. So this is the solution to the IVP for this particular problem. Okay, let's do one more of these IVPs and then we'll call it a day. So let's say we have dy over dx is equal to e to the 2x over y squared. And we know that y of 0 is equal to 3. In general, it doesn't have to be 0 to be the initial value. Of course, that is a common scientific measurement that's easy to grasp because you will often have a starting value, right? Y of 0 would be occurring at time 0. Again, this is easy to separate. We have y squared dy would be e to the 2x dx, and then we can integrate both sides, so we end up with y cubed over 3, and this would equal e to the 2x over 2 plus a constant, so really just a two-step problem to actually solve the dE. Now we want to plug in that point, so we would know that 3 to the 3rd over 3 would equal e to the 0 over 2 plus our constant. So 3 cubed over 3 is just 9, and e to the 0 is 1, so if we subtract 1/2 from both sides, we end up with 17 over 2 as the value of c. So that's the solution to our initial value problem here. Y cubed over 3 equals e to the 2x over 2 plus our 17 over 2, constant that we solved for from the initial value. Okay, so that is it for the separable differential equations. Again, the technique is not so hard, just a little bit of algebra via multiplication and division to separate the variables, and then from there we just use our integration techniques to go ahead and solve. If you have an initial value problem, you have to plug in the points and find the value for c. Anyhow, this is Dr. Lennon signing off.